Imagine a Friday morning in New York City. You enter a futuristic train terminal, not an airport, bound for London. Instead of a plane, you board a train inside a transparent tube. The doors close and you accelerate into a tunnel beneath the Atlantic Ocean. You're not crawling, you're flying through a near vacuum propelled by magnetic forces at over 8,000 kilometers per hour. The ocean's crushing pressure is held back by engineering marvels. Through reinforced windows, you glimpse bioluminescent creatures in the darkness. The ride is smooth, quiet, and so fast you barely finish a movie before arriving. Breakfast in Manhattan, lunch in London, no jet lag, no turbulence. This is the promise of the Transatlantic Tunnel, a 3-hour journey connecting continents. It's a vision that could shrink our world, making business, family, and adventure as easy as a daily commute. But how could we ever build such a thing? The idea of a tunnel beneath the Atlantic has fascinated dreamers for over a century. Inspired by feats like the transatlantic telegraph cable, visionaries wondered, if we can send messages, why not people? Today's boldest concept is the vacuum-sealed Maglev train or VAC train. By removing air from a sealed tube and using magnetic levitation, friction nearly vanishes, allowing speeds faster than jets. The technology exists in small forms, but scaling it for a 500-kilometer ocean crossing is a challenge like no other. Turning this dream into reality means facing obstacles on a scale humanity has never seen. Building a tunnel across the Atlantic would be the most daunting engineering project ever. The ocean floor plunges deeper than Everest is tall, with crushing pressures and shifting geology. The tunnel would cross the volatile mid-Atlantic ridge, home to earthquakes and volcanoes. Construction would require fleets of robots working in total darkness, freezing cold, and powerful currents. Every stage, from surveying to assembly, would be remote, battling corrosion and constant danger. The logistics of moving materials and coordinating thousands of machines over thousands of kilometers are staggering. Safety is a colossal concern. A breach at these depths would be catastrophic. The scale and danger are almost unimaginable. To grasp the scale, compare the Transatlantic Tunnel to the Channel Tunnel, 50 kilometers long and 75 meters deep. The Atlantic Tunnel would be over 100 times longer and deeper, making the tunnel look tiny. Even the Great Wall of China and the International Space Station pale in comparison. The materials required, steel, concrete, advanced composites, would strain global supplies for decades. Every component must be flawless to withstand the ocean's relentless force. The cost? Estimates reach up to $20 trillion, more than the annual GDP of the US or EU. Financing and building it would demand unprecedented global cooperation. Could we build this tunnel? Today the answer is no. Technology, materials, and funding all fall short. But impossible is a moving target. Air travel and smartphones were once fantasies too. Breakthroughs in materials, AI, and robotics could one day make such a tunnel feasible. What's impossible for us may be routine for future generations. For now, the Transatlantic Tunnel remains an inspiration, a challenge to push the limits of human ingenuity. If it existed, would you take the 3-hour ride beneath the ocean or stick to the skies? The future, as always, is waiting for us to build it.